um, a link to the group as well as the LinkedIn group for SecIG. You're welcome to take a look at what we've been doing in the past few years and participate in these activities. I am the chair of the founding chair of SecIG of TCCN, and Professor Dola Saha here. She is the vice chair, one of the vice chairs. The other one is Charles Clancy. So today I'd like to welcome Dr. Poor, who really does not need any introduction in our circles because of his seminal work in physical layer security. So Professor Poor is the Michael Henry Strater University Professor of Electrical Engineering at Princeton, and his interests include information theory, machine learning, network science, and their applications in wireless networks, energy systems, and related fields. He is the NAE, he's a member of the NAE and the National Academy of Sciences, and a foreign member of the Chinese Academy of Sciences and the Royal Society. Recognition of his work includes the 2009 Comstock Edwin Howard Armstrong Award and the 2017 Alexander Graham Medal, and honorary doctorates from universities in Asia, Europe, and North America. So I will not stand any more between you and his wisdom. So I'd like to welcome Professor Poor.
Thank you, Suba, and good morning, everyone, or good afternoon, or good evening, depending on where you are. I see lots of familiar names on the screen, so thank you all for joining. It's an honor to be the inaugural speaker in this series. I was just talking to Dola about some of the future talks, and I really look forward to listening to those as well. But I'm happy to be the first one. And let me see if I can share my screen. That's an important part of this. There we go. Can everyone see can you see me?
Yes.
Okay, great. And let me just see, can you see the changes? Let me see. Yes?
Yes.
Okay, good. All right, well, again, good morning, afternoon, evening, everyone. Thank you for joining. Dola invited me to give this talk, and she asked me to talk about physical layer security. So at the time, I was thinking I might talk very broadly about not only about all aspects of physical layer security, but then I realized that that was probably more of an all-day talk than a one-hour talk. So I decided I would focus in on those aspects of physical layer security that are related to information theoretic ideas. So that's really going to be the focus of my talk. I don't know if you can see these things on my screen, but I'll try to get rid of them. Yeah, so I'm going to focus in on information theoretic things. I'd like to thank three people in particular who helped me with putting together this talk. One is Ursi Chordi from INSEA in Paris, and Madi Herfa, who's one of her students, and also Miro Mitev from Essex, one of her former students, I believe, or postdocs. And a lot of what I'm going to say today can be found in a chapter that's maybe to appear, or perhaps has already appeared very recently, in a book on physical layer security by Koa Le, and it's co-authored with Madi and Ursi as well. So let me just say a little bit about put physical layer security in a bigger perspective. So, you know, today we have a pretty good security architecture for wireless networks. We have, you know, of course, wireless networks are organized into layers, and those layers above the physical layer are secured by various tried and true methods. Okay, so you know, we might ask the question, why do we even need physical layer security? And the answer is in, I think, emerging technologies, not so much in existing technologies, but in emerging technologies. So, you know, sort of a standard way of securing a wireless link is at the higher layers using cryptography, right? And there are a lot of good things about those methods. First of all, there are no known feasible attacks, widely employed, tested. Most of us are completely happy to do banking and so forth with what we have today. Authentication is trustworthy and so forth. There's a long history of success with these methods. There are some negative things. One is, though, it's, of course, modern crypto is built on unproven assumptions about the difficulty of certain computational problems. And with the emergence of quantum cryptography, quantum computing, some of those assumptions may fall away. Also, it makes an assumption that the physical layer is already there and established. They can be computationally intensive, which can be a disadvantage, for example, for Internet of Things terminals, which might be low complexity. And they require significant infrastructure. That is, you need to do key management and key distribution and so forth, which requires you to have a pretty serious infrastructure to support the wireless network. Now, physical layer security has overcome some of those advantages. First of all, it's quantum secure because it's based, at least what I'm going to talk about today, is based on information theoretic principles. Key can be generated in the network. It doesn't have to be necessarily require infrastructure for key generation. And it's fast and lightweight. So basically, physical layer security, or at least some of the aspects of physical layer security, require very light computation. So it's more like channel coding than it is like encryption. Of course, there's some disadvantages. You may have noted that physical layer security hasn't taken over the world of practical networks yet. And that's because of some disadvantages. We often need to know something about the eavesdropper's channel in order to get to those provable results. There are some issues about finite block length. I'm going to talk a little bit about that today. And again, it's still in its infancy. That is, even though some of the ideas have been around for decades, this is still an area of technology that needs quite a bit of developing. And I'm going to talk a little bit about that at the end as well. So, as I mentioned, one of the things that we, let me see if I can, there we go, it's better. One of the things that we, that is motivating the interest in physical layer security are new applications. And the prime one is the Internet of Things. So I think I don't need to tell this group what the Internet of Things is. It's enough to know that it's much more massive than the mobile internet, for example, which is upper bounded by the number of people. The Internet of Things is only upper bounded by the number of things, which is, orders of magnitude more than the number of people. The terminals could be, there could be very light infrastructure. The terminals could be very simple. The purposes of IoT are not necessarily media transfer, but it's more, inference, sensing, decision making, and so forth, machine learning, and what have you. So it's a totally different group of application scenarios, a massive size, massive scale, and much more diverse type of terminals and infrastructures out there. So, IoT security is a major concern. There's a lot in the press about it. If you think about IoT being in your house with Nest or Ring or those kind of applications, there are a lot of possible things that can go wrong. Okay, and of course, IoT, healthcare is one of the big potential applications, and so forth. So there are many concerns about IoT security and privacy. And I'm going to talk, by the way, although the title of my talk is about security, I'm also going to talk a bit about privacy because I think it's closely related, particularly in its information theoretic, from an information theoretic viewpoint. So just an example of what can go wrong with IoT. This is from a paper from Usenix from a couple of years ago with Sali Sultan and my colleague Pratik Mittal. So Sali is at Amazon now. So this is we looked at what might happen if a botnet were to get control of a lot of IoT devices, say Nest devices, controlling things like air conditioners and refrigerators in people's homes. And it turns out that with a Mirai-sized botnet, so Mirai was a big botnet that brought down the internet a few years ago. If you have the same scale of botnet, you can controlling water heaters, you can change the demand in the grid instantly by 3 gigawatts, which is the same as having access to the largest currently deployed nuclear plant. So it's like you could turn on and off a nuclear plant instantly. And of course, the grid is not set up for that kind of jolt to the system, either on or off. It always is trying to balance load with generation. And this would cause major disruption to the power grid. And that paper has a lot of examples of that. Of course, this is not happening today. There's probably not 600,000 water heaters out there that can be controlled. But in the future, when all of us have, IoT control of our houses, this is something that has to be thought about. So the point is here that security in IoT is a big driver of something like physical layer security. So what can physical layer security offer? Well, there are 3 things that we think about when we think about security: message integrity, authentication, and confidentiality. And I'm going to focus in this talk mainly on confidentiality, but I'll say a little bit about some of the other things at the end. So there are a lot of things in the physical world that can address these. I mean, for example, just the physical characteristics of wireless terminals are unique. And so we can use those physical characteristics to uniquely identify or authenticate devices. I'm not going to talk about that today, but this is certainly a very important part of providing security based on physical layer characteristics. In the area of message confidentiality, which I'm going to talk about mainly today, we have, going back to the 70s, we have this notion of Wiretap channel, which tells us about how we can think about these kind of questions, issues, information theoretically. And that has given rise to a tremendous amount of research in the last decade on physical layer security for message confidentiality. And I'm going to talk about some of that today. Also, as I mentioned, key generation can be on the fly when you take advantage of the physical layer. I'll talk very briefly about that as well. So here's an overview of what I'm going to talk about today. So first of all, the theme, as I mentioned at the beginning, is just a role for information theory in this area. That's what I want to focus on today. There's a whole lot more to this area, and I'm not saying it's not important. It's just not what I know much about, and also I think it's as I said, it's really too much to talk about in 1 hour. And I'm going to focus again mainly on message confidentiality, and I'm going to add privacy to that. And because of the close relationship of the 2 problems. And I'll talk about message confidentiality and data transmission first, and then I'll shift and talk a little bit about privacy and sensing systems. And then at the very end, I'll just mention a couple of things, other things, authentication, security and mobile ad hoc networks where you don't have infrastructure, and some information theoretic discussion about that problem, and also about some attacks on sensor networks, which can also be viewed in context of physical information theory. So let me start then on message confidentiality in transmission systems, and I'll just repeat a couple of things that I just said in a different context. So the whole idea of physical layer security is to rethink security design. Okay, and as I said early on, it's really been a higher layer issue, and it's involved things like encryption, key distribution, and things like that, authentication and so forth. Okay, as I said, when I mentioned IoT, if you have a massive number of devices and very little infrastructure, low cost, low latency, applications and terminals, you know, this is a problem. These issues are problems, or these features are problems for conventional types of security. So again, physical layer security provides security by taking advantage of what's out there in the physical world. In the case of data transmission, it takes advantage of noise, fading, and so forth, which are naturally occurring things in all communication or in all wireless links. And we can exploit those, or at least in principle, we can exploit those to obtain some degree of message confidentiality. And in the end, what we're thinking about doing in this particular aspect of physical layer security is to take what we do traditionally in wireless links, that is error control coding, and add for reliability, and add some features to give us security. Okay, so that's really one of the ways of thinking about physical layer security, at least from the viewpoint of the things I'm going to talk about right now. So, you know, the idea of using information theory to think about security goes back to our founder, Shannon. And in his, not his 1948 paper, not his foundational paper, but his 1949 paper, he looked at the idea of using information theoretic principles and quantities to describe the security of a cipher system. So this is not the kind of system I'm going to talk about mainly today, but you know, he looked at a 3-terminal system. You have a message M that Alice wants to transmit to a legitimate receiver, Bob, reliably, while keeping it secret from another terminal, Eve, an eavesdropper, at the same time. And in Shannon's model, which is a ciphertext, encipherment model, Alice and Bob share a secret key. And so he was interested, by the way, in a real system from World War II, which was used for communication between Roosevelt and Churchill, which was a one-time pad a radio telephone system. So that's what he had in mind, that kind of system. And this describes a system like that analytically, very, very precisely. And so what Shannon showed, and so he described secrecy in terms of information leakage between Alice and Eve. And he showed that for a cipher system like this, you can get perfect secrecy. That is, you can transmit the message perfectly to Bob and keep it perfectly secret from Eve. But you can only do that if and only if K has at least as much entropy as the message M. That is, you need a one-time pad. So this is sort of good news and bad news. The good news is that you can get perfect secrecy in such a system. The bad news is that you need to have a one-time pad. Now, in the system that Shannon was interested in that I mentioned, they did have a one-time pad. They had it. It was on a record, a long-playing record. They would record some noise or something in Virginia, impress a couple of these, put one in Washington and one in London, and then they had a one-time pad. And that one-time pad was carried on a back channel, which was some kind of agent who carried it strapped to his wrist over to London. Now, in wireless, we don't have that luxury because we don't have a back channel. We have to transmit the key the same way we have to transmit, or we have to develop the key the same way we have to develop the message. And so that one-time pad idea is not really very viable. Now, very few crypto systems actually use one-time pad. Most of them have a smaller piece of key whose entropy is lower than the entropy of the messages. That key is blown up. It's actually a crypto variable, right? That's blown up into a key whose entropy is really the entropy of the original variable, not the entropy of the message. And so the entropy of the key is typically much less than the entropy of the message. And therefore, these systems are not provably secure in the sense of Shannon, even though they are secure under the assumptions that certain computational problems are too difficult to solve practically. Okay, now this is in 1949, so quite a long time ago, 70 years. If we move forward, the next, let's see here. The next thing that happened in this area was in the 1970s, also quite long ago, when Winer introduced the Wiretap channel. The Wiretap channel has the same three terminals, Alice, Bob, and Eve, but it doesn't have the shared secret key, okay? Instead, Winer recognized that the Wiretap channel, that actual communication channels have noise, which of course Shannon knew too, but he was ignoring it in his model for other reasons. And in this, and because of the noise, we might be able to get some, do some secret data transmission by taking advantage of that noise. So that was really the question that Winer asked. Can we take advantage of the noise in the channels, imperfections of the channels, if you will, in order to transmit secretly to one terminal, keeping it reliably to one terminal, keeping it secret from another. And he looked at particularly at the reliable rate from Alice to Bob, which is the classical information theoretic quantity, versus the so-called equivocation of the message at Eve, which is just the conditional entropy of the message given Eve's measurements. And what he wanted to do was to look at rates at which Alice could transmit to Bob reliably, keeping the equivocation at Eve equal to those rates. So that would be perfect secrecy. And he was interested in particular at the maximum rate, reliable rate to Bob, such that that rate R equals to the equivocation at Eve. So that's what he called the secrecy capacity. And Winer also had good news and bad news. The good news was that, in fact, the secrecy capacity can be positive in such a system. You don't need to share a secret in order to transmit in secret. But it's only true, it's true if and only if Z, the eavesdropper, is somehow degraded relative to Y. That is, Eve has a worse channel than Bob. Okay, so that's the bad news. The good news is secrecy capacity can be positive. Bad news is, that only happens if Eve has a worse channel than Bob. And can we guarantee that? Okay, so zoom forward to our days. There's been a resurgence of interest in these ideas, and that's why I'm here talking to you today. In general, there are two lessons from Shannon and Winer that we have to always keep in mind, is that we can transmit messages in secret, but we have to have some advantage over the eavesdropper, either a shared secret like in Shannon's model, or a better channel like in Winer's model. So the question is, how can we get that without sort of the infrastructure of encryption? Well, we can take advantage, as I said earlier, of the physical properties of the radio propagation. That is, the principal physical properties are diffusion, that is, waves diffuse out into space, and superposition, that is, at the point of reception, any waves out there are going to be added together. And so these provide opportunities for basically either sharing a secret or providing a better channel to the legitimate receiver. So for example, fading, which I'll mention again briefly in a minute, provides natural degradedness over time. And I'll talk about that a little bit more later. Interference, this is the superposition property. It allows active countermeasures to eavesdropping, that is jamming. Okay, you can jam an eavesdropper. Spatial diversity, which comes about from both of these properties, diffusion and superposition, using MIMO, relays, or what have you, can allow us to create secrecy degrees of freedom, which then allow us sort of like certain channels, or we can slice the channel, if you will. We'll have certain channels that are secret, can be kept secret from eavesdroppers. Also, there's common randomness out there. We have random channels between terminals, and they're, because of the reciprocity of wireless transmission, Alice and Bob can see the same channel from two different sides. So that gives and it's random because of the diffusion and superposition properties. And it's different from Eve's channel. So they can share a secret, or they can derive a secret from a common secret from that shared randomness. So these are physical properties that give us hope that we can do something without heavy encryption to provide reliable and secret data transmission. Okay, so now the first of these three properties have been investigated in detail, and they give develop so-called secrecy capacity regions for all of the fundamental channel models used to understand wireless networks. In particular, the broadcast channel, which was very, very closely related to the wiretap channel, multiple access channel. So broadcast channel, of course, one transmitter, multiple receivers, multiple access channels, multiple transmitters, one receiver, interference channels, multiple transmitters and receivers. All of these problems have been studied in a quite bit of depth in the terms of their the information theoretic security aspects of these channels, leading then to ideas about physical layer security in these channels. So broadcast, of course, is like downlink, multiple access is like uplink, interference, of course, is multiple base station networks, for example. And of course, other channels, relay channels, MIMO channels, and so forth, all of these have been studied in the context of, mostly in the context of Weiner's original idea of trying to determine secrecy capacities or generalizing into secrecy capacity regions. And I'll just point you to this paper at the bottom from the Proceedings of the National Academy of Sciences with Raphael Schaefer, which goes over a lot of this material in some depth. I'll just give you an example. This is the broadcast channel. It's actually the Kerner and Cesar broadcast channel with confidential message, the BCC. So this is a broadcast channel where Alice wants to send messages to both Bob and to Eve. So we'll think of Eve as being a second legitimate receiver in one case. And there's two messages, one message, which is a broadcast message, M1, and there's another message, which is a confidential message meant only for Bob. Okay, so you might think about here as a content distribution network. This is a model for a content distribution network where you have some terminals which are receiving all the content and other terminals that are just receiving the premium content. So for all the content, all receivers are legitimate, and for the premium content, some receivers could be thought of as eavesdroppers because they haven't paid for that content. So we can, if we look at the Gaussian case where all the channels are additive white Gaussian, we can look kind of quickly at the basic idea here. If you look on the horizontal axis at the rate of the common message, and on the vertical axis is the rate of the secret message. This is a case where Bob is advantaged over Eve. The signal to noise ratio at Bob is 10 dB, at Eve it's 5 dB. And you can see the red line there is the capacity region of this broadcast channel without any imposition of secrecy. But if we impose perfect secrecy on the second message, you can see that the so-called secrecy, the capacity region, by the way, is everything underneath the red curve, of course, in the general case. And in the secret case, the capacity region, the secrecy capacity region, that is the joint rates, reliable rates of both messages to Bob while keeping the second message secret from Eve, is all the potential pairs underneath the blue dashed line, or I guess it's probably purple dashed line. And you can see that there's some capacity in here. I don't know if you can see my pointer, but there's some capacity in here which has to be used up to achieve secrecy. And I won't go into that in this talk, but the way that secrecy is achieved is you use some of the code words to basically confuse the eavesdropper. And the capacity needed for those code words is that capacity that's lost here to eavesdropping. Now, some of that capacity can be recovered. In fact, all of it can be recovered if you have multiple antennas, but I'm not going to get into that in this talk. There are other papers on that, which are described in that paper with Raphael. Now, if we just look at what happens as we change the quality of Eve's signal, that is, we vary her signal to noise ratio. So as it decreases, the common rate, that is the rate on the horizontal axis, declines because the bottleneck for that message is going to be Eve's ability to receive that common message. And of course, as her signal to noise ratio declines, that's going to be harder and harder to transmit reliably. On the other hand, as Eve's signal to noise ratio declines, it's easier to transmit a secret message. So the secrecy rate gets better. So you can see what happens as we degrade Eve further. It makes it worse for the common message, but better for the secret message. It's kind of intuitive. Now, in this problem, Wiener would tell us, if Eve's signal to noise ratio ever gets to be 10 dB, then the secrecy capacity region will collapse. And that's because of Wiener's bad news in that you really have to have a degraded channel in order to get secrecy rate. Now we can get around that in a way by looking at the fading broadcast channel. Same channel now, but instead of, and both channels are additive white and Gaussian with units, 5 dB signal to noise ratio in this case. But now the channels are fading. They have Rayleigh fading on them. So Bob's channel, or Bob 1, I call it here, his channel, is fading with Rayleigh fading with parameter 1, and Eve's channel is Rayleigh fading with parameter sigma 2. So if you remember your Rayleigh fading, as sigma 2 gets smaller, Eve's channel gets more, it's a degradation of Eve's channel, okay? And you can see here the same thing happens as the fading gets worse on Eve, the common rate gets smaller, or the range of common rates gets smaller, which is on the horizontal axis, and the range of secret rate gets higher. Okay, so this is very similar to what happens in the Gaussian broadcast channel with different signal to noise ratios. But a big difference here is that, in fact, for this channel, the secrecy capacity never goes to 0, even no matter whether Eve's channel is degraded to Bob's channel or not. So for example, you can see that the red line here is the case where the two channels are statistically identical. And there's a pretty healthy secrecy capacity region there. So that's a distinction when you have fading, just like in the case of ordinary data transmission. Fading can help a lot with reliability, of course, and diversity. It also can help with security, at least in the physical layer. And that's for the same reason, basically. Diversity, that's because fading, this is a fast fading channel. There are times, even despite the intensity of the fading, there's always going to be times when Eve is degraded, no matter what value of sigma 2 there is. Sometimes Eve is going to be degraded, secret messages can be transmitted. So anyway, so that's sort of a very simple, basic way to think about one aspect of physical layer security. Now I want to talk about another thing which relates to IoT in particular, and some of the things that are emerging in 5G and beyond 5G networks. And I'll do that. I'll first go back to Wiener's channel, the Wiretap channel. So here's another way of looking at it. We have Alice. We have a channel with Alice. There's one channel input. There's two channel outputs, one going to Bob, the legitimate receiver, one going to Eve, the eavesdropper. And what we look at, in Wiener's model, just like in Shannon's models, we have an asymptotic formulation. That is, the block length goes to infinity, the probability of error at Bob goes to 0, and the information leakage at Eve goes to 0. Okay, so that's kind of the asymptotics of Wiener's model. And in this case, very nice formula for secrecy capacity, which is just the maximum over the input distribution to the channel of the difference between the mutual information between X and Y and the mutual information between X and Z. So that is mutual information between Alice and Bob and mutual information between Alice and Eve. This is within certain conditions. There's a broader formulation which gives some other, a more general formula, but this is a way to think about it, okay? So this is a very nice, clean formula. It's just like Shannon. It tells intuitively what's going on here. But one of the problems with this is that this is an asymptotic theory. And I think most of you know that we're now talking about, particularly in IoT, about short block length, low latency communication. So we have to wonder, what does this tell us about that? Okay, so I want to talk a little bit about that problem, and then I'll move on to something else. Okay, so I'll remind you something you hopefully have seen before, which is work with Yuri Polyansky and Sergio Verdu on finite block length information theory. Okay, so here I'll just very briefly mention this to you. Here we have a source. This is a classic problem in information theory, right? Or in communications for that matter. You have a source, it has m possible values that can be transmitted. So there are log2 of m bits in that source. Source is called W. It's encoded into n symbols that can be put into the channel. The channel manipulates those symbols in some way, distorts them, and out comes yn channel outputs. Those go into a decoder, and the decoder tries to recreate the transmitted symbol W, okay? And what we'd like to do, in Shannon's model, of course, we'd like for W asymptotically, the error in between W and W hat to go to 0 as the number of channel uses n goes to infinity, okay? So in particular, we're interested in looking at n, m, epsilon codes, where n is the channel block length, m is the number of possible values of the source, and epsilon is the fidelity of recreation of the source at the output of the decoder. And of course, the fundamental limit is the maximum m we can choose for a given block length and a given error, upper bound on the error of reconstruction, okay? And we know, of course, that if we take the log of m star and let n and n go to infinity and epsilon go to 0 and divide by n, we get the capacity. That's one of Shannon's fundamental results. But what if we don't do that? So in IoT, for example, we don't have n going to infinity, epsilon going to 0. We have finite block length. And with finite block length, it turns out we can well approximate log of m star by this formula that you see here. So the leading term is, of course, n times the capacity, as it has to be. The next term is root n times v, another quantity, times the q inverse, q being the tail of the standard Gaussian distribution, evaluated epsilon, plus higher order terms. The only new term here is v, which is the dispersion. So the capacity, of course, is the expected value of the information density evaluated at the optimal input distribution and the corresponding out distribution. That's Shannon's result. And the dispersion is the variance of that same random variable. Okay, so it's very intuitive that the second order term is going to depend on the second order moment of the information density. So this is a 10-year-old result going back to Yuri Polyansky's PhD thesis. And it's pretty good. I mean, so here's the additive white Gaussian noise channel, 0 dB, epsilon equal 10 to the minus third. So remember, epsilon is the quality of reconstruction. And this is chosen so that these numbers are chosen so that the capacity is a half. And here you can see the rate, which is the log2 of this m star over n versus the block length n. And in this paper, there's a converse bound and an achievability bound. And so the actual capacity, so the Shannon's capacity, the asymptote, is a half, but the actual capacity for finite block length is somewhere between the red and the blue line. So you can see there's quite a gap to capacity here, and particularly for those short block lengths that come up in IoT, that is for low latency, short block length communication. Block lengths are going to be in the hundreds, not the thousands. And so there's going to be a gap to capacity. Even for block length of 2000, you see there's a gap to capacity. So capacity, as we know it, is really a very long asymptotic quantity. So what about for physical layer security? That's a sort of in the Shannon context, but what about in the Wiener context? Well, the issue of physical layer security at finite block length has also been looked at much more recently. This is with another colleague, Wei Yang, now at Qualcomm, and Raphael Schaefer appeared last year in the information theory transactions. And so we look at the same model that Wiener had, but we don't let the block length go to infinity. So we let epsilon, which is the reconstruction error at Bob, delta, which is the information leakage at Eve, we let those be finite and non-zero. And we let n, the number of channel uses, also to be finite. So then we have a secrecy rate, just like we have a reliability rate in the other problem, R star, which depends on these three parameters: block length, quality of reconstruction at Bob, and information leakage at delta. And what can we say about that? Well, just as in the Yuri Polyansky's work, we can look at upper and lower bounds on that rate. And I'll just give you a couple of examples. Here's one for the so-called semi-deterministic wiretap channel. I don't know if you can see this, where delta equal epsilon equal 10 to the minus third. Trying to get rid of that thing, put it down there, it's better. Okay, semi-deterministic means that the legitimate channel is deterministic and the eavesdropper's channel is the binary symmetric channel in this case. I think the crossover probability is 0.1. I don't have it written here. I don't see that. But in any case, you get a similar result here. This formula, you can see it. It's very, very similar to the formula for the ordinary data transmission. There's the secrecy capacity. This is Wiener's capacity. And then there's the dispersion again, and so forth. Okay, and now we get delta and epsilon appearing there, and you see that here we get this again a very tight converse and achievability bounds, which shows us that for small, for short packets, there's a big gap between the actual secrecy capacity, the asymptotic version of Wiener, and the actual secrecy capacity. This actually appeared in an ISIT paper in 2017. Now, we can also look at the Gaussian wiretap channel. There are bounds also in that paper that I mentioned from IT there. This is, oh, I see I did a typo at the top. This is a degraded case. This also has epsilon equal delta equal to 10 to the minus third. I didn't put that there. You can see here that the achievability and converse bounds are not as tight, but still they still point to a considerable gap to the actual secrecy capacity. Okay. I mentioned that we can also use the common randomness given by the channel to distill key between Alice and Bob. And there's a lot of work in this area going back to Yuri Maurer in the 1990s, using things like public discussion channels, which can also be seen by the eavesdropper, taking advantage of channel reciprocity, which I mentioned earlier, or in fact using trusted or even oblivious relays to help create key. Also, there are situations where you can have an active eavesdropper trying to disrupt the process, and then you can take advantage of channel reciprocity. Okay, so There's a lot of work in this area. I'm not going to discuss it here today. Some of it is mentioned in that paper. That is discussed in that paper I mentioned at the beginning. There's also a chapter here from a few years ago, which talks about some results to that date. Excuse me. Okay, I see I'm running out of time, so I'm going to speed up a little bit on the next bit of things. So let me talk now a little bit about privacy in sensing systems. And this really also thinking here about IoT as the main application, where we have private data of people being handled by IoT devices, and that privacy needs to be protected. So I'll just point out that privacy is different from security. Alice, Bob, and Eve is in the secure model. In this case, Eve is a malevolent actor. But in the case of privacy, we don't necessarily have a separate eavesdropper. We have a legitimate terminal, Bob, who we may want to preserve some privacy from. Okay, so this is not an eavesdrop. This is not a wiretap channel. This is an ordinary channel. It's just that we have information that Alice has some information that she would like to keep confidential from Bob, okay, not necessarily from an external eavesdropper, while communicating other information directly to Bob. Okay, so, there's kind of a trade-off Alice has in such a situation between denying access to whatever information she has, which provides secrecy, but on the other hand makes a data source useless. Sorry about this. Allowing Bob to see all of her information, which would completely violate whatever privacy there is there. So there's a trade-off between these two kinds of things. All right. So there's a lot of reasons why we might worry about this. Smart metering systems, motion sensors in our houses, other things in our houses that might, cameras and so forth, that might reveal private information about us. Of course, as I've just trying to say on the previous slide, the usefulness of this data depends on its accessibility to whoever's supposed to use it, right? Which is sort of Bob in our parlance. But accessibility endangers privacy. So there's a fundamental trade-off in privacy between the privacy of data and the utility of that data. And that can be characterized by information theoretically. And I'm not going to go into a lot of detail there, but I'll just say that, they're sort of, you can think of utility, for example, in terms of distortion, or as an inverse property to distortion. And you can think of privacy as being something like equivocation. That is, the greater the equivocation at Bob, the more private the data. On the other hand, the greater the distortion at Bob, the less utile the data is. And you can actually construct utility privacy trade-off regions using these quantities. Something like rate distortion function. It's like rate distortion theory with an equivocation constraint. You get a boundary. So the outer boundary is something like an efficient frontier. And it doesn't tell you necessarily where to operate. It just tells you what the trade-off is. So once you decide how much privacy you're willing to give up, that tells you how much utility you can expect in the best case. So an example of this is smart metering. Smart meter data, of course, is ubiquitous these days in many parts of the world. It helps utilities price electricity on the spot market, balance load, and so forth. So it has a lot of utility, but it leaks information about in-home activity. So that is, in particular, the trace of a smart meter can be used to make inferences about what's happening in the home. But it turns out that we can do a trade-off with a certain modeling of the trace, and we can see an information theoretic, a very, very common information theoretic result ensues. In particular, if we model the intermittencycy very of usage with a hidden state Gauss-Markov model, it turns out that we can get a very common type of solution here, which is reverse water filling. That is, if the usage, if we look at the spectrum of the trace, those frequencies with low power or low energy are suppressed by the encoder, and those with high energy are allowed through by the encoder. This reverse water filling solution actually gives the optimal trade-off between utility and privacy in this case. It's intuitive that if you're interested, the things that are most revealing are transient behaviors, and those are the low energy ones that are being suppressed. And of course, if you allow the water level to go up and down, you trace out the trade-off between privacy and utility in this case. I think given time, I'm going to skip the next example, which is another way of trading off information leakage in a system, a more complicated system with energy harvesting and a battery and storage. So the storage can basically be controlled to trade off the utility and privacy. But I'm going to skip that just because of time. I'm just going to mention here also another problem, which is competitive privacy, where you have a network of interacting but competing agents whose measurements are coupled, and they all have their own task. Say they're trying to estimate their own state. So this is again like an IoT application, and they get utility from sharing data, but then that also compromises privacy. So they're like, each one of these agents has a privacy utility trade-off, but it's all competitive. So you want to ask the question, how should they interact? And again, so just some examples, sensor networks where you have maybe two different oil companies exploring for oil. They can find it better if they share measurements, but then of course they're giving up some of their own information. You know, you might have radars out there with different allies with a common enemy, but maybe they don't trust each other so well. Electricity grids, you have, utility providers, electricity providers have to work together to keep the grid stable. On the other hand, they're competitors, and so they have some desire to keep certain information private. So these kind of examples give you these competitive privacy problems, and with a certain simple formulation of a linear measurement model looking at utility in terms of mean squared error, so again, a distortion measure, and looking at privacy in terms of information leakage, so again, information theoretic measure of privacy between different agents. It turns out you can do some nice analysis. This turns out to be a Wiener-Ziv problem, which tells us how to exchange information by using Wiener-Ziv coding. It doesn't say much about how much information should be exchanged. That's the province of game theory. There's a lot of interesting game theoretic issues here, and it reveals the need for things like pricing, cooperation, and so forth in order to enforce certain privacy utility trade-offs that are beneficial for everyone. I'm sorry to go so quickly over that, but I do want to come in on time. So just mention very briefly a couple of other issues, and I'll go over these quickly too. Other problems have been studied in an information theoretic context, authentication, where we can look at bounds on impersonation and substitution attacks. This is some work with Li-Feng Lai and Hesham El-Gamal from the 2009. We can look also at attacks on manets, mobile ad hoc networks, where you don't have infrastructure, where you have some malicious nodes. We can look at the scaling of secrecy capacity. This is work with Yingbing Liang and Lei Yang. Lei Yang. We can also look at attacks on sensor networks in this context. This is work with Zhang and Rick Blum. And this looks at some effects on not necessarily on Chimera lower bound, which is a type of information theoretic quantity and parameter estimation of these kinds of attacks. And I'm going to skip over the details of these just to get to the end, because I don't want to impose on your time much more. So let me just close with some thoughts. First of all, hopefully I motivated the need and the promise of physical layer security. And I focused in on information theoretic ideas because the field is so big now that it's hard to talk about all of it in one talk. Even you see here, I ran out of time with even these information theoretic ideas. I'll just point out that, again, something I mentioned at the beginning, this is really theory. They do point to practical solutions sometimes, like, Wiener-Ziv coding, for example, shows up. It's not exactly practical, but there are distributed source codes out there. But there's a lot that needs to be done to make this real. One is a lot more finite block length analysis if we're thinking about IoT in particular. Scaling laws for large networks. A lot of what I talked about was for like simple 2-3 terminal networks. You need really to think about very large networks for massive deployment like IoT. Practical coding schemes. There are some out there, but really a very limited amount of work's been done there. And then other security primitives, signatures, certificates, and so forth. To really do physical layer security, you've got to do the whole security suite to make it viable. Okay. I want to point out another thing here, which is that, one of the things about physical layer security is you might think of it as being kind of a best effort kind of security. So some applications really need ironclad security. For example, banking. Or e-commerce, other types of e-commerce, or warfare, right? Military applications of security. These have to be ironclad because you can't allow any leakage of information. But for some applications like media distribution, maybe sensing, so forth like that, things like that, you really don't necessarily need ironclad security all the time. I mean, for media distribution, for example, if you're distributing video, you don't really every bit doesn't have to be secure. As long as you can disrupt the video enough so that no one wants to watch it, you've really achieved your goal with security. So we can think about, like we do quality of service, we can think about quality of security as a parameter. And so physical layer security is one way of providing certain level of quality of security. Okay, it may not be ironclad. You may not want to do your banking with the Wiretap code, but you might not mind distributing content with a Wiretap code or putting it on your Nest devices and so forth. So that's something to keep in mind. And then I'll just mention some references, which I'm going to share these slides, so I won't put them up here. Maybe I'll leave them up here for a minute, but I want to go down and point out one I didn't talk about, which is this one with Simi Yagli and Alex Ditso, which was presented at SPALK earlier this year. Of course, one of the big applications, one of the big aspects of IoT is the use of machine learning. And machine learning, one type of machine learning is federated learning. And one of the issues in federated learning is privacy. So initially, federated learning was said to be privacy preserving. It's since been shown that that information does leak through in federated learning. And information theory can also illuminate that problem. And this paper, and we're working on some other things along these lines, looks a little bit at the use of information theory to look at privacy leakage in federated learning. I didn't have time to talk about it today, but I think that's something also of interest. And with that, I'm done, and I'm happy to take questions if we still have time.
Thank you so much, Professor Poor. It was wonderful.
Yes, thank you.
Great, thank you. I don't know if we have time for questions. I don't know what the protocol is here.
So I think we can take the questions, and if people needs to leave, they can. But we would really like to answer some of the questions that we have over here in the chat window. I can read out from the very top. So this is from Burak Ozupairaz. How realistic is that Eve is aware of the Alice-Bob channel?
So Eve is aware of the output of Bob's channel. Well, that's a good question. So, it depends on the scenario, right? I mean, if you think about Eve as being, think about a wireless network, which is what we're talking about here today. And, you have two terminals out there in the field. And of course, because of diffusion, Alice's transmitter is going to send out a signal that's going to be received by Alice and Bob, okay? But I mean by Eve and Bob. Now, those are not going to be the same channel output in general. So it's not really, I wouldn't really think of Eve as receiving the same thing as Bob, although that's in Shannon's model, that is the case, right? So maybe that's what Burak is referring to. In Shannon's model, he ignores the imperfections of the channel and just assumes that Eve can directly observe Bob's output, the output to Bob, right? That's what Wiener was trying to get away from with his Wiretap channel. In general, that's not the case. I mean, you'd have to be sitting right on top of Bob's receiver to receive the same thing. In fact, you have to be inside Bob's receiver because of the thermal noise to receive the same thing. So I think in general, there's not an assumption that Eve is receiving exactly what Bob is. That's really I would say a theoretical construct. It's really not the physical layer, right? It's at a higher layer. Shannon's model you might think of as being at the bit pipe level rather than at the at the actual physical level. So I hope that answered the question. It's a good question, but I think it's a different point of view in Shannon's model where he's thinking purely about the issue of the encipherment, not so much about the physical channel.
Sure. The next question comes from Marco Hernandez. Dear Professor Poor, thank you very much for your presentation. Look, I've been involved in IEEE wireless standardization activities like 822.11, 822.15, etc. As there is a compulsory clause on security over the years, once in a while we have received physical layer security proposals. However, invariably such proposals are dismissed as academic curiosities. One reason is that assumptions and implementation complexities are difficult to realize in real implementations. Could you please comment on how to effectively implement physical layer security protocols? Thank you.
Yeah, that's a great, Marco, that's like the $64,000 question, right? How do we implement these things? So what information theory tells us is that there is something there, right? There's something there to be exploited. What it doesn't tell us is how can we exploit it? And that's really what standards are about, right? Is how do we exploit something that we know is there? And so far, I don't think we have an answer to that question. I think people are working on that, but we haven't gotten to that point. Now, one of the things, though, I do want to emphasize, particularly with regard to something like 802.11 and even for mobile phones, there we look at a very high level of security, right? So I mentioned at the end this idea of quality of security. So if you really want to have ironclad security, and I think that's what Wi-Fi is looking for in their standards, as is 5G and so forth, you're going to have to use some kind of encryption, right? I mean, I think that's just the only way to do it right now. Now, maybe someone is going to develop some ideas later that will make that comment inappropriate. But right now, I think that's the way it is. So right now, what do you have? You have wiretap codes and so forth. So those can be used, but they're not going to give you the same level of security that you're going to get with encryption standards, right? So the idea is to get away, at least I think, at least in the short term, is to look at situations like IoT where you're not going to be able to apply those standards. You're going to have to use some kind of security light. And then, you've already said your quality of security is going to be lower. It's a lower parameter than for something like Wi-Fi. And now can we provide that level of service using physical layer security? So I think that's the way I would think about it, Marco, in the short term. In the long term, I don't know. This is a research area. I mean, information theory came out in the 40s, and it was a long, long time before anybody got to capacity, right? It was really, turbo codes, in 1990s, right? So that's what, 50 years. So, I don't think we should write this off because it's a curiosity. I think it's, it points to an opportunity. And as engineers, we should be trying to exploit that opportunity. That's the way I look at it anyway. It's a great question though, Marco. Like I said, it's the main question, I think, with physical layer security.
Thank you. So the next question comes from Ning Shi. As we know, the existing PLS schemes can deal with eavesdropping attacks. My question is whether the PLS can defend against some active attacks or not. For example, impersonation attacks or substitution attacks. If yes, how?
I think there are, that's a great question, Ning. Thank you for that. So I guess, let's look at physical layer security in the large, not just the information theoretic things that I talked about, okay? So then you get into these physical unclonable functions, signatures of devices, and things like that. So you can have an enrollment period, and there's also biometrics, by the way, so that's another whole area. So if you can have an enrollment period for devices and people, then you can start looking at things like that, okay? I don't think the information theoretic ideas necessarily address that problem. So I certainly didn't talk about it today, okay? There may be other work that I'm not aware of, but I think then, look at some of these other issues where the physical characteristics of devices are used, and the fact that you can't exactly, no two chips are the same, no two cell phones are the same, regardless of the manufacturing tolerances. So that's the kind of thing you have to get into, I think, when you're talking about those kind of issues. That's a great question.
And to add to that, our next month's talk is on RF fingerprinting. So this is going to talk about, our next month's talk is all about how to find the RF fingerprinting of the devices.
Okay, so that's a perfect example of that. It's not really information theoretic, but it is physical layer security.
Correct, yeah. So the next question comes from Tariq Haider. Hello, Professor Poor. How complicated are the secrecy achieving Wiretap codes? Thank you for this interesting overview.
Yeah, hi, Carrick. Thanks for the question. Actually, the codes are not too much different from error correcting codes. So I think that's one of the advantages for IoT is that Wiretap codes, well, let me back up from that. Okay, the codes in the proofs are just like the codes in the proofs of Shannon's results. They're random codes, right? So they're very complicated. But the actual codes that people have worked on to try to devise practical codes are like LDPC codes and that sort of thing. So they're like error control codes with other properties, and the code words are chosen in such a way and used in such a way to give you protection against the eavesdropper. So I don't think I think low complexity is one of the advantages of physical layer security, at least in terms of data transmission.
The next question comes from El Mehdi Ili. Thank you, Professor Poor, for the very rich talk. To the designs of the current and upcoming wireless networks, 5G and beyond, take into consideration in the recent releases practical solutions or techniques for enhancing PLS in addition to improving reliability of the communication? So the question is, do they actually take care of that?
Oh, I don't know if 5G. In fact, we had that question earlier from Marco. He might be able to answer that better than I am. I haven't followed closely the latest standards activities. Of course, 6G is, it's a research area right now. It's not a standardization area. So I think maybe there is some discussion of physical layer security in the 5G standards. I don't know how definitive it is. 6G, I'm hoping, because of the issues I mentioned, you know, the IoT, the massive deployments, you know, the ultra reliable, low latency communications, all these issues point to something besides the current solutions for secrecy. So we'll see. I mean, maybe quality of security will become a, you know, one of the features of 6G, in which case I think physical layer security has a significant effort. By the way, that term quality of security I learned from Ursi Chordi, who I mentioned earlier. I think she's on this call. I think it's a really great way to think about security going forward.
The next question comes from Muhammad Osman. PLS is generally between two devices directly connected over the wireless channel, while the security we assume in the internet is between systems. Are there any efforts to use PLS-generated keys in end-to-end systems?
Oh, that's a great question, Mohammed. I don't, you know, that's a great question. I've been looking much more at just the actual down in the physical layer links. Okay. Once you get above that, I don't really know much about what's going on, and I'm a little doubtful as to whether you could think about the end-to-end system in a physical context, because there's just so much in between, right? There are routers, there's all kinds of links and so forth. You know, so you know, it's hard for, you know, I don't want to say no, but it's hard for me to conceive of these ideas applying an end-to-end link over a, you know, very complicated network with the base stations and infrastructure, backhaul, and all that stuff. I think I'm thinking mainly about what's happening right down there, you know, where the rubber hits the road in the physical layer. Maybe you could think of something though, Mohammed. If you can, that's great.
Sure. So the next question comes from Mohammed Faruqi Azam. Hi, Professor Poor. Thank you for very interesting talk. I will be thankful if you can comment on the effect of energy harvesting relays on physical layer security. Are there any benefits?
Well, that's thank you, Mohammed. So you know, there's another thing I mentioned very briefly, which is the role of relaying in physical layer security. And there is a lot of possibility for relaying. Both trusted and untrusted relays can be used, at least in principle. You know, I haven't really seen, though, that's a great idea. I haven't really seen energy harvesting enter into that analysis. I don't know that it would, well, it certainly would alter the analysis. I can't offhand think about how. I mean, maybe in the same ways that energy harvesting would generally alter relaying. But it's a great question. As far as I don't know of any work, and someone on this call may know of work in that area. I don't know of any work yet where energy harvesting relays comes into this analysis. But certainly it's important to think about, because in IoT, we're going to have energy harvesting, right? So that's another important feature which I didn't talk about today. I think it's an interesting one to contemplate.
Our next question comes from Jody Boris. Hi, Professor Poor. Thank you very much for this great talk. The cognitive channel can be studied as a particular case of the interference channel. So I assume that the results for PLS in the IC can be somehow particularized for this cognitive channel. However, in the overlaid cognitive paradigm, secondary users serve as a relay for the primary ones just to keep the required SINR. Is there any known or studied limitation of this paradigm in terms of PLS? Is there any way to trust the secondary user?
Yeah, there is, by the way, some work on the cognitive interference channel. I can send a reference if Jody, if you want to email me, I'll send you a reference on that. There has been some work in that area. Yeah, and it is a one-way cognitive channel. So one channel is aware of the other's message, but not in reverse. So I can't remember all the results exactly. It's about 10 years old, but there is a paper in that area that I can share. So my email address, by the way, was on the first slide, and it's Poor, my last name, Poor, at princeton.edu. So Jody, if you just send me an email, I'll send you that reference.
Also, I have another question. This is from Mehri Mehrina. Thanks for a great talk. Does energy harvesting threaten the security of the network? Can it lead to information leakage?
Well, Mehri, I think that's a good question. I think it goes back to Mohammed's question about the relays, energy harvesting relays a little bit. You know, I don't know how much work has been done specifically on energy harvesting, some perhaps, but I think the answer is yes, it would, because it just puts another constraint, right, on the system. So the more constraints you put, the smaller the region of possibilities, you know. So just intuitively, I would say yes, but I can't point to any particular work that's shown that. But I think intuitively you'd have to expect, you know, the whole idea of intermittency and so forth that you get with energy harvesting is certainly going to have some effect on the secrecy rates and so forth.
So I do not have any more questions from the audience. I just have a quick question if you have some more time.
Sure.
I know that we have been running a bit late. So my question is that as we are moving more towards millimeter wave and terahertz channels, we see different kind of fading in terms of, and then there is almost no multipath when we are looking at very directed terahertz links. So how do you think that physical layer security can help in there, or if there is a different way that we need to think of fading in terms of physical layer security?
Yeah, another great question. Thank you. So, you know, directionality can be your friend, right? In this area, because if you have an eavesdropper, I mean, if you think about a classical situation where the eavesdropper is another terminal, if you have a very directional signal, it's going to be very hard for an eavesdropper to be there, right? I mean, for example, a related type of issue comes up in massive MIMO systems, where you get very directed beams, right? As you let the number of transmit antennas go up, and the beams get narrower and narrower, it's harder and harder for eavesdroppers to get in there. So if you have randomly distributed eavesdroppers and randomly distributed legitimate terminals, and you're using massive MIMO to communicate with those legitimate terminals, it gets harder and harder for those eavesdroppers to get a good signal. So I think that's going to, you know, I think things like terahertz millimeter wave are like kind of like massive MIMO in that respect, because you have a very directed signals, right? So I think that's only going to be helpful in terms of security. In my view, I mean, I think of course someone is going to figure out a way to maybe to eavesdrop on that, but it's almost like a direct line of sight without any opportunity for someone off to the side to get in there and intercept signals. So
sure, yeah. Thank you.
Thank you, Dola.
Thank you for this wonderful talk. And can we get your slides?
Yes, absolutely.
Okay, then we will take this slide and the recording and post it in the SIG website.
Thank you.
And at the very end, I would like to thank from all the community that you've taken your time to discuss all these information and give us a path to where the research should move forward to. So thank you.
Thank you, Dola, and thank you all for listening to my talk and for your questions. And on the slides, there will be my email address. If you have any comments or questions or ideas, I'd be happy to hear from you. So thank you very much.
Thank you.
Good day, good morning, good evening, good night. See you.
See you.
Bye-bye.
Bye.